Hi there, everybody, and welcome to this week's Astro Coffee Hangout. My name is Tony Darnell. I'm from deepastronomy.space, and today, if you're not getting ready for the eclipse, then I don't know what else you're doing, because it's the biggest astronomical event to hit the United States in quite a while, so we're all very excited about it. And today, we're going to be talking a little bit about what professional astronomers are going to be using the time during totality for. It is a remarkable time, both not only for us who get to just observe this very amazing astronomical occurrence, but it's also an important time for professional astronomers. We'll talk about why that is, but what the main reason has to do with looking at the atmosphere of the sun. During a total solar eclipse is one of the few times we can get up close and personal and see the faint, tenuous, wispy atmosphere of the sun known as the corona. It's millions of times fainter than the disk of the sun, and it is very difficult to see. But we have lots of ways in which we do it artificially, both on the ground and in space, and we'll talk about that as well. But we'll also talk about what an eclipse offers professional astronomers, and you'll also get an introduction into the corona itself, some of its properties, as well as why it's an important part of the heliosphere, which is the space around the sun that is influenced by the sun, which is obviously also important to us as well. So we're going to be lots of great things to talk about. We hope you're getting ready. If you want to, we're going to answer your questions and comments about the eclipse as well with professional astronomers that we have on hand today. But before I do, let me start by introducing my co-host, Dr. Carol Christian. Hi, Carol.
Hey, how are you?
I'm good. It's good to see you again. So why don't you introduce our Hangouts a little bit? You're still here.
Sure. On behalf of the American Astronomical Society and the American Astronautical Society, we bring you
I like what you said that.
Astronautical. We bring you afternoon astronomy coffee. The idea is it's much like sitting around, chatting, having coffee, and talking to some of the researchers who are members of those professional societies and what they've been up to as far as their research, what they're thinking about, what they observed, how they're analyzing their data, what they found, and what they are going to do next about it. So we're glad to have our guests who've been working on a specific situation with the sun.
That's right.
The topic of the month.
Okay, yeah. So we hope that you guys will ask us questions and comments on the live chats on whatever platform you're watching this on. I'm monitoring all of them, so is my good friend Carl Clark, and we will answer your questions and get to your comments throughout the course of the Hangout. So today's research, we are going to be talking with a couple of astronomers from the National Solar Observatory. Let me get them up now. My guests today are Dr. Claire Raftery. She's the Director of Education and Public Outreach at the National Solar Observatory. And also in the upper right panel there is Dr. Gordon Petrie. He is a scientist also at the National Solar Observatory. Now, welcome, guys. And
Thank you.
You guys apparently have, you're predicting what you think the shape of the solar corona will be during the eclipse coming up on August 21st. But before I get to your predictions, let's give our viewers a little bit of a background into what the solar corona is. Maybe one.
Yeah.
Which one?
What's
which
a
one?
Solar corona? Exactly.
Which one? Gordon, can you give us some background on the solar corona?
Well, during an eclipse, the corona is the bit you can see around the disk. It's really thin and wispy. It looks a bit like a crown, hence the name corona. During very active phases of the sun's magnetic field cycle, this corona looks very spiky, complex. During a quieter phase of the sun cycle, it looks completely different. It looks almost symmetric. The streamers out the sides, and a very dark hole at each pole of the sun. The corona is a very tenuous gas. It's very highly magnetized, ionized, and the plasma emits. And because the plasma emits and is trapped along magnetic field lines, we can use this emission pattern of the plasma to infer what the magnetic field is doing. And we can see the closed fields of the solar corona much more clearly than the open fields because the closed fields trap the plasma, so the plasma can't escape as the solar wind, whereas at the open regions of the corona, the fields that are open out to the heliosphere and beyond, the plasma simply escapes thermally as the solar wind. So this is why during different phases of the sun's magnetic life, the corona can look so very, very different. It's just a reflection of the magnetic field there.
Now, I've heard it said that the coronal the corona, the region above the solar surface, which by the way is itself kind of tenuous, isn't it? We've got what we call the photosphere, which is where a lot of the photons come out from the sun. Above that is another layer called the chromosphere. That's sort of a really low. Is that characterized as kind of an atmosphere level itself? It's not really the surface of the sun, right? It's
a sort of intermediate layer which has its own very distinct characteristics.
Right. It's just above the photosphere, which is that what people mostly think of with the surface of the sun is the photosphere?
Well, the photosphere is the visible surface in visible light. We look at the photosphere.
It's not an easy question, is it? I mean, where exactly is the surface of the sun?
Not at all, and it's not well defined. It's very temperature dependent, and there is a convention which fixes that for scientists, but it is arbitrary.
Yeah, and then of course the layer above that is the solar corona above the chromosphere, and these all have different temperature ranges. The photosphere around 5,500, I think.
That's about right.
Is that about right? And then the chromosphere is like 7,500 Kelvin, or I'm sorry, is it Celsius or Kelvin? Celsius.
Well, at this level, it doesn't matter.
Who cares? It's plus or minus 270 degrees, whatever. And then, but this is not insignificant. The solar corona has a much, much higher temperature, doesn't it?
Yeah.
How hot is the corona?
It's crazy and it's unexplained, but the corona is 1 million or several million Kelvin.
That just blows me away. I mean, it's so much hotter than the surface of the sun, right?
So I had a question, Gordon. So suppose that the sun had no magnetic field. Would the corona just be a bunch of streamers going straight out? Would it just be a wind?
You'd expect more of a Newtonian cooling profile of a gas.
Which is? Explain what that is.
Basically, the temperature would decrease with distance from the sun. And the solar wind wouldn't be accelerated, and life on Earth would not be possible, basically. So we do appreciate the coronal field, even though we can't explain it.
Wow.
Yeah, that was one of the things that I felt was very counterintuitive. How much hotter the solar coronal temperatures were than down on the surface. However, the densities are a lot less, aren't they? I mean, we're talking about particles in the plasma here that are much, much less dense than you would see on anywhere near the corona, right? Or the chromosphere.
And this allows the magnetic field to dominate this plasma so that when the plasma emits, we can kind of see what the magnetic field is doing.
Okay.
That's not possible in other parts of the sun.
Well, I think this is a good time to inject your image that you were talking about, and we're going to go into a lot of details on this. But Carl, if you could pull up that one image from the press release, and then we'll sort of follow up a little bit more with some of the topics that we just introduced. There we go. There we are. Okay, let me pull this up big. Get rid of that. Okay, so here is a drawing of. Well, you tell us, Gordon. What is this a drawing of?
Well, this is a graphic of selected magnetic field lines around the sun. The sun, of course, is the dark disk, which we've made it dark to make it look like an eclipse. And the lines around the circumference of the disk, these are the magnetic fields which I'm suggesting carry the plasma that we'll be able to see during the eclipse. Now, this is based on data taken exactly a rotation before the eclipse occurs. So instead of August 21st, where we don't have data, I've grabbed data from July the 25th, and exactly one rotation early, so that we have a basic idea of what the corona looked like then. The assumption is that it'll look pretty similar on August the 21st, because the global physics of the corona is generally quite slow. So
Okay. Yeah, so there's a lot there that I want to get back to, but the point I want to bring up here is that the corona, the shape of the solar atmosphere is drawn or dictated by these magnetic field lines. It shapes how it looks, and you're trying to predict the shape of this atmosphere of the corona by looking at it one solar rotation earlier and then assuming that it doesn't change much over that period. But the point I wanted to make here real quick is that the sun is highly magnetic, and so much of what goes on out in this region of the atmosphere is dictated by that magnetic field. You said earlier, and Claire, I'd like you to also comment on this a little bit too, if you could. The sun goes through a solar cycle of activity. Can maybe one of you explain what that is about and how long it lasts, and where we are in this eclipse in the solar cycle?
Yeah, why don't I jump in with that one?
Okay.
So the sun has a solar cycle that is dependent on its magnetic field. So the magnetic field that you see in Gordon's image here, this is embedded in it's rooted underneath the visible surface of the sun in a region we call the tachocline. And as the magnetic field protrudes out through the surface, it protrudes through regions that we know as sunspots. The reason we get sunspots is the surface is being pushed out of the way, so it appears like it's darker than the surrounding areas. In actual fact, it's just that there's less material in those regions. And the time scale over which this happens is on the order of years. So the magnetic field let me step back a little bit. So the sun rotates differentially. And what that means is that the equator rotates faster than the poles. And this ties back to the fact that there's no solid component to the sun. It's not like it has a crust like the Earth. It's gas the entire way through. And so as the equator rotates faster than the poles do, the magnetic field is trapped in with these gases. It's frozen in. And the magnetic field starts to get wrapped up around the equator, north and south of the equator. And as this happens, the magnetic field becomes magnetically buoyant. There's just too much magnetic field wrapped up around itself, starts to protrude through the surface in these sunspots that I mentioned a few minutes ago, in these very large magnetic loops. And they range from the order of the size of one Earth to many Earths, such as the loops that you see in Gordon's graphic here. But this is not really stable. As we all are aware, nature likes to be in its lowest energy state. Things like to be in their most stable state. And so having all of this pent up magnetic energy is not stable. And so over time, the magnetic fields interact with each other through a process called magnetic reconnection. And it's a bit like an electrical short. So the magnetic fields interact, they touch off each other, and they reorient themselves in such a way that they start to relax and they become more stable. And the magnetic field starts to move closer to a regular bipolar magnetic field, which is very similar to what we see with a bar magnet. So you have magnetic field coming out of one pole, wrapping around like a butterfly type shape and in through the other pole. And that whole process takes on the order of 11 years. And this is what we call the solar cycle. Really, the solar cycle is 22 years because during this process, the magnetic field polarity also flips. So as the magnetic field starts to relax, the magnetic fields actually start to migrate towards the north and south pole, and they actually cancel out the predominant polarity at these two poles. So over 11 years, the magnetic field of the sun will go from being north-south to south-north, and then over the next 11 years, it will repeat that and go back to north-south. So it's a 22-year cycle officially, but we are more familiar with it as a sunspot cycle, which is an 11-year process. So as the magnetic fields become tangled and they start to protrude through the surface, this is where we really start to see more and more sunspots show up. So the sunspots are the indicators that these magnetic fields are really tied up and they're coming through the surface. And then over the next 5 or so years, and as they're relaxing, the number of sunspots decreases. And so this is why we call it the sunspot cycle, because it's an indication of how complex the magnetic field is at any given time.
And you can see this if you look yourself at the sun. Let's say you do some solar projection of a telescope onto a blank piece of paper. In fact, it used to be the old days. In fact, they did this in Boulder back at NOAA back a long time ago. Was they would draw on a piece of paper the sunspots that they could see for that given day, and then they would keep track of this. And of course, you can see more sunspots during solar max than you can during solar min. Where are we now in the solar cycle?
Go ahead, Gordon.
Sorry, we're in a declining phase of an activity cycle. So we're in this sort of hybrid state where the sun is still quite active, but not very. And the characteristics of a solar minimum corona are actually developing visibly. So you can see in this plot that especially in the south, you have a very nice, simple polar coronal hole, as we call it. It's the fields that are fanning out into the open space around the model. This is a clear characteristic of a minimal corona, where the coronal field looks a bit like a bar magnet, as Claire described, with the two poles very simply defined. In the north, the situation is really very different, actually. You can see some open field lines, but you can also see a lot of bright closed loops there. This is because the two hemispheres of the sun, the north and the south, are actually out of phase at the moment, just at this precise moment of the cycle. The north hemisphere is lagging the south by maybe a year or two, and while the north has already quietened down, has developed this minimal configuration looking like a bar magnet, the north is looking a lot messier, especially in this plot where the closed loops are drawn in so brightly.
Okay, hang on. You said that the north is dragging behind the south by about a year or so. You mean in terms of activity?
Yes.
Oh, okay. All right.
So about something like a year or two ago, the south looked like what the north does right now.
And so we're on a declining edge toward min then, right? Solar minimum?
Exactly. In another couple of years, maybe 2020, late 2019, 2020, the sun will look like a very simple, symmetric magnetic structure, something like a bar magnet.
Okay. So we're on the declining phase of solar activity now. In a few more years, we'll probably be closer to the minimum now. So the sun rotates, you said this earlier, Gordon, once every 27 days or so, correct?
That's right.
And, okay, Carl, if you wouldn't mind, maybe stop sharing your screen so I can get everybody back on. And so what you guys did was you looked at the solar corona about 27 days prior to the 21st to look at what one solar rotation earlier from the solar eclipse would look like. How did you make this observation? With what did you look at the solar corona with?
So, yeah.
Yeah.
So I think I understood that. So my branch of...
I'm such a great interviewer.
My branch of the observatory observes the solar surface magnetic flux distribution, magnetic field strength, basically, all the time. This is because certain parts of the government need information on the sun 24 hours a day, 7 days a week. So my branch puts out these data series automatically all the time. It has telescopes, six telescopes strategically arranged around the longitudes of the Earth, such that at any given time, at least one of them is observing the sun. So I grab these data from the solar surface and I make a map, a full surface map out of them, 360 degrees longitude, 180 degrees latitude. And I extrapolate a model for the coronal magnetic field from these surface data using a mathematical technique, which has become standard. And it's this model that you actually saw in the plot. I integrated field lines through this model, selecting the field lines according to the density of the magnetic flux, the strength of the field, and whether the fields are open to the heliosphere or closed back down to the surface. So that's all I showed you there. And the assumption is that over a single rotation, the global corona, while it changes a bit, inevitably, it doesn't change too much for this model to be invalid as a prediction. Now, this isn't a completely safe prediction because if a giant active region were to appear during the last rotation before the eclipse, then the global coronal field, the general appearance of the corona, could actually change quite a lot. But I'm assuming that nothing so dramatic will happen.
Now, when you say active region, you mean basically another sunspot, right?
Exactly.
Yeah. So they can pop, they can kind of come and go, but because we're decreasing in the activity cycle, it might. You're thinking maybe not so much of a danger of that happening.
I'm sure something will pop up, but it has to be a really large one or lots of moderately sized ones to make a big difference.
Okay, so you looked at the solar corona through all these telescopes that you mentioned, made this map, made this drawing, one full solar rotation prior to the eclipse. Now let's say the eclipse is coming along and you observe it and you're right. What information, let's say it matches exactly what you're predicting it will be. What will that tell you? What will that be? Something that
it'll tell them it's time to pop the champagne.
Well, I have another answer to that. Actually, I will be.
I'm sure.
I will be insufferably smug to an extent, but inside I will be disappointed because I'm sure the sun is not that simple. I think, however closely the model resembles the corona, and I do expect differences. But even if it's fairly accurate, I expect the differences to be very interesting. For the model makes a lot of simplifications so that somebody like me can do such a model. One of them is that the fields at the photospheric level are almost vertical, and the fields right above the photospheric level are almost relaxed, almost totally relaxed into this current-free, force-free configuration. And I know for sure that both of these assumptions are simplifying assumptions. They're not literally true.
Okay, I want to try and say that again to make sure I understand it. You're saying you're assuming that the field lines close to the surface of the sun are vertical, but a little bit higher up. Close. A little bit higher up, you say they're relaxed. The chromosphere, presumably, they're what? Relaxed? What does that mean?
Actually, above the chromosphere.
Above the chromosphere.
Yeah, the chromosphere is actually abstracted into a current sheet in this model, which is another simplification. But the main simplification is this transition from a nearly vertical field in the photosphere to an almost totally relaxed minimal energy state field in the corona. And it's a very nice simplification of what's happening in the sun because it is generally almost always true, which is why the model works at all. But the extent to which that assumption fails is very interesting physically. So if I see any problems with the model compared to the eclipse, the direct eclipse observations, that's where I'll be directing my attention.
Okay, good. So you're hoping to get more information to refine your models.
Yes.
If you're right, on the one hand, you're going to be smug but disappointed because, excuse me, that your model has made some simplifications that can't be complete.
Yeah.
And then, but if you are wrong, then you can zoom in on the differences between what your model predicted and what you observed during the eclipse to see how to improve your model.
Exactly.
Okay.
I'm also going to jump in and say that I think.
Oops. Oh, I'm sorry. I accidentally muted you when I clicked on you.
No worries. I think a lot of solar physicists are secretly hoping Gordon might be wrong, because I think we're all hoping that a very large active region may suddenly appear in the run-up to the solar eclipse, in the hopes that we get a coronal mass ejection on eclipse day. That would be everybody's solar physics dream, that we actually have a CME erupt during totality and we're able to observe that, especially with some of these nationwide projects where you have distributed observers from coast to coast, and we would have 90 minutes to observe a CME. So that's the dream, but unfortunately, that also means that Gordon's model may not be accurate.
So do I understand that if you have people observing that, it's very quick? I mean, what any one individual observer on the Earth would see would be very quick. And so then you have to patch that all together. Is that what you do?
So each location across the path of totality will only get about 2 minutes worth of totality. And so you can't see much during 2 minutes. You can ooh and ah and appreciate it in the moment. But as far as collecting data, 2 minutes is not a very long period of time. However, there's a few different projects. One of them we're running out of NSO. It's called Citizen Kate, and it's been led by one of our scientists, Matt Penn, who will be, I think, in Weiser, Idaho on the day. But he has 68 different sites spread all the way across the entire country. And each of those sites will get about 2 minutes worth of totality, but it's been set up almost like a relay race. So as totality passes from one observer to the next, the observations are being taken up by the next person. And so each of these sites are on the order of 100 kilometers or so away from each other. So it's far enough away that each observer will get a decent period, be able to see the shadow for their 2 minutes of totality, and then the next person is ready to take up the reins. So the idea here is that at the end of the day of the eclipse, we'll have 90 minutes worth of totality. And we're not the only nationwide project. The Eclipse Mega Movie is another program that is inviting people to take pictures of totality and contribute to their movie. There's a few other citizen science projects, the names of which escape me now. Citizen Joe-ham, I think. I apologize. But there are a good few citizen science projects that are depending on people's contribution to their success that require the nationwide data collection.
Has there been anything like this before where you've gotten 90 minutes of total observations during totality? Has there been anything like this before? Not that I know of.
There have been a few. So from the scientific perspective, the region of the atmosphere that we're really able to access during an eclipse that you can't really access the rest of the time is the very lowest layers of the atmosphere. So those very lowest layers of the solar corona, during totality, we're able to image them reliably. Normally, when we try and image this part of the solar atmosphere, we're using coronagraphs, which require the use of, I'm sorry, my mind is letting me down. Pardon?
Occulting discs.
Occulting discs. I was going to say attenuators, but I knew that was not right. Occulting discs. And the occulting discs create anomalies close to the edge of the field of view, which is this region that we can finally see during the eclipse. And since the distance between the sun and the moon are far enough away, we're able to take these observations reliably all the way down to the solar surface. And so this is one of the real benefits to being able to do this. So as far as I'm aware, this 90-minute period of totality hasn't been used to study the dynamics of the sun to this degree in the past. Of course, there are a lot of very reputable astronomers who have been taking observations during eclipses for decades. And every time they see the eclipse or see an eclipse, they're able to further our understanding of the sun and the corona. But the benefit of this period is that even though we get eclipses about every 16 months or so, mostly they're in really awkward places. They're over the ocean, they're over the poles, or somewhere that you can't get to easy. This time we have a huge continent that's highly populated that we're able to place people to go and actually take these observations.
Well, I'm happy to hear that you, or maybe Matt Penn, whomever, has got this long chain of observers to be able to maximize the total time of the eclipse. So that's going to be extremely exciting. I want to get to some of our questions that people are asking on the chats, but before I do, I want to just talk about two things. I want to ask about the wavelengths at which scientists are interested in viewing the corona, and then I want to talk a little bit about space-based versus what's so great about an eclipse on Earth. So let's start with the wavelength. What wavelengths are you guys going to be imaging the corona in?
On the day of the eclipse?
Yeah, on the day of the eclipse. To get those images of the corona, what wavelengths are you going to be looking at?
We'll be imaging in white light, so we'll be just using the visible spectrum on the day of the eclipse.
So no big filters to like H-alpha or any of that? You're just going to be looking at white?
No, we will have 2 of our sites that will be using polarizers. And so this is a potential test bed for the 2024 eclipse that's coming up that potentially will have polarizers all the way along, polarized telescopes all the way along the path of totality. But for this eclipse, most of our sites are just using very high quality white light detectors.
Okay. Carl, can you please put up Matt Penn's picture that was on Facebook? Because I want to go to the next part here. So we have ground-based observatories. Gordon's already talked to us about these. Mauna Loa Solar Observatory has been taking images of the corona since. Here, let me pull this up. Has been taking images for decades in white light, as you put, and there's a model here. In the upper left is actual data from Mauna Loa Solar Observatory, where they use a scanning linear CCD to go all the way around the limb of the sun, and they take that's the actual solar corona. They do it every day the sun is not cloudy, and even many days when it is, and you get a rough idea of the shape of the solar corona from this. However, it's blurry. It doesn't go very far out. Gordon, do you recall how far out in solar radii is the Mauna Loa field of view?
It's only a few, I think.
Yeah, it's not very far out, okay? But this is from the ground, okay? And you can see the shape, the coronal holes, the shapes of the big features like that are shaped by the magnetic field of the sun. But you don't see anything like what Gordon has here, the NSO-B extrapolation frame, which has got a lot more detail in it, and you would be able to see a lot more. So my question is, why... This is still one of the most scientifically useful astronomical events that can occur on Earth. And I wonder if you could comment on why solar physicists get so excited during an eclipse. What is it about an eclipse that lets you get a view unlike any other time?
So besides the aesthetic thrill of seeing the corona with your own eyes, you see parts of the corona that you can't see otherwise in white light in all wavelengths, all visible wavelengths at the same time, right down to the surface. The reason why that's so exciting is that almost all of the most beautiful and spectacular solar phenomena, also the most frightening phenomena from the sun, originate from very low in the solar atmosphere. So I'm talking about flares and mass ejections, which sometimes make the news for taking out satellites or power grids or that kind of thing, turning cities dark. This is the nightmare scenario of solar physics, is that a major event happens in the corona, a massive ejection or energetic particles are directed straight at Earth and do enormous damage. So besides the aesthetic side, we desperately want to understand the physics of what's happening low in the solar atmosphere, and the eclipse gives us a very direct view of that level of the solar atmosphere, which we don't normally get.
And another thing I wanted you to comment on. The reason I'm trying to lead you toward this is that it's also a time when we can do these Mauna Loa observations every day, all day long, but right. They still have a bright sky background, don't they? You still don't. It's during an eclipse that you can get rid of the actual sky noise, the background noise too, correct?
Yeah, so much light is scattered from the sun that it takes, even though the solar atmosphere, the corona, is 1 million or more times dimmer than the disk itself, so much light is scattered that it's very, very hard to eliminate this light in a coronagraph observation. We still don't know how to do the optics. The best coronagraph we have is still the moon, just because it's so large and far away.
Yep. Okay, Carl, if you could stop sharing that, I'll bring everybody back in. All right.
Can I add one little thing to the discussion here about the bright sky background? So one of that's definitely a challenge of ground-based coronagraphy. one of the things that we're trying to do to overcome this will be implemented on the Daniel K. Inouye Solar Telescope, which will be getting its first light at the end of 2019 or 2020. And what they're doing there, instead of looking at the corona in visible light, they're actually going to look at the corona in infrared light. So by going to the infrared, the sky is much, much darker. So it looks like the night sky. And so the quality of the images, the relative contrast, all of these are much, much stronger. And so we're able to do the kind of coronography that we can do from space, but all the way down to the surface.
Yeah, in order to try, that's a great example. Thank you. And that telescope is going to be really exciting. I can't wait for that thing to start seeing first light. But imagine the problem like this, folks. You're trying to image on a bright, sunny day, just a tiny, and even this is an exaggeration, a high cirrus cloud, and you want to get as much detail as you can from that while in the middle of the day. The sky background is so high that it's hard to differentiate the signal between the two, and that's the real challenge. During an eclipse, the sky gets dark because we're in the shadow of the moon, and that cuts away so much background noise that boom, the solar corona just pops right out at optical wavelengths, which is where they're planning on viewing this thing. And it's one of the few times where now we can mimic this by using occulters, like Claire said earlier, in blocking out the sun's light with the disk, but that still doesn't do much for the sky background. So if you go into space, Claire, you want to comment on what we do in space, what we have up there to maybe see, and is that better?
Sure. Well, I'm not going to say that any one thing is better than the other. I think the way that we can do our best science is by combining all of these different tools, because they all help to fill in another piece of a very large and complicated puzzle. So what we have in space are, we have coronagraphs also in space. These are mostly looking at white light emission as well, so the visible images. And these are these telescopes. So the primary telescope that we use as research scientists right now is the LASCO instruments on SOHO, the Solar Heliospheric Observatory, and also the two coronagraphs on the stereo mission. So Stereo A and Stereo B are two satellites that were launched going on 10 years ago now, and they're going in opposite directions around the sun in their own orbits. So if I'm at Earth, then these two are gone this way around the sun. They've actually crossed over on the backside of the sun and are now heading back around towards the Earth. And each of those have coronagraphs on them as well. The nice thing about the stereo instruments is that they do what it says on the tin. They can provide images of CMEs in stereo. So by looking at a CME from this projection and also from this projection, it gives us three-dimensional information that we can't get from a two-dimensional projection like we can with just a single instrument. And so these space-based coronagraphs, the nice thing about them is that they're constantly pointing at the sun. They don't have to worry about being on the nighttime side of the Earth. So at nighttime, our Hawaii telescopes won't obviously be able to see the sun. SOHO is at L1, and so it's at the first Lagrange point between the sun and the Earth. And as I said, the stereo missions are they have their own orbits directly around the sun, so they're not in the shade of the Earth at any stage. I alluded earlier to the limitations of some of these, that because they're space-based, the physical distance between the detectors and the occulting disks is fairly small. You can't launch something that's long enough to be able to minimize the edge effects that we see with a coronagraph. However, that is partly where scientists are hoping to go. They're hoping to fly formation satellites, possibly on CubeSats, where they will have the detector on one satellite and they will have the occulting disk on another satellite, and the two of these will fly. They'll be unconnected. They won't be physically connected in any way, but that they'll fly in formation and be able to do similar kinds of things that will give us better resolution lower down at the edges of the field of view.
Great. Okay. Thank you, Claire. So Adam Synergy is commenting, thank you, Moon, for being an awesome coronagraph. And that's true. But I have a question related to that. Isn't the Earth in a rather lucky position to be? We're one of I think the only body in the solar system, and I wanted to ask some actual astronomers this, where we actually get to see this kind of an event. The moon just happens to be the same exact apparent size in the sky as the sun does. Does that happen anywhere else in the solar system?
So I can't say for certain, but I did read a piece recently that suggested that one of Jupiter's moons was also the same apparent size as the sun in the sky. But of course, Jupiter has no solid surface, so it's not like anybody could go to Jupiter to see a solar eclipse from there. So as far as a habitable planet, yeah, the Earth is the only place that you can see a total solar eclipse. And bear in mind, it's not only the fact that we are on the Earth; it's the fact that the moon and the moon and the sun have elliptical orbits, and so otherwise, if they didn't have elliptical orbits, we would get a total solar eclipse every time we got a new moon. So every time the moon passed between the sun and the Earth. But because both the moon is the moon's orbit is at a 5-degree tilt, and the moon is in a slightly elliptical orbit, as is the Earth, sometimes the moon appears to be smaller in the sky than the sun, and this is what results in an annular eclipse, and sometimes it's larger. And in actual fact, for this eclipse, the apparent size of the moon will be slightly larger than the apparent size of the sun, but not so much that we'll be able to tell. But there's a very, very subtle difference between the two of those. So it really is a very fine dance. And not only are we not only are we in a lucky position, geographical position, to be able to see this from the Earth looking at the sun, but also we're in a very fortuitous time in the Earth's existence, because as the moon's orbit changes, this will no longer be true. The moon is moving away. It's going to look smaller in the sky. And so at some point in the future, only annular eclipses will be possible. So
that's right.
Very fortunate.
I read that somewhere. The moon is gradually increasing its distance around the Earth, and in like 250,000 years, there's going to be no more total solar eclipses. They'll all be annular, like you said. So there's a lot going on. That's very true.
Yeah. It's a very lucky time to be alive.
Yes, it is. So Willie Yee is asking, would stereo observe any sunspots that emerged on the far side during the eclipse?
Oh, yes.
Yeah,
they would see the sunspots as bright patches, bright loop-shaped structures. Sunspots, as Claire described earlier, they sort of emerge as pairs of opposite polarity, joined by loop-shaped magnetic fields, and it's the loop shapes that you would see often in very complex formations. And if the structure is small or the resolution is bad, you'd see this as a bright patch.
Okay.
Data.
Now, Andrew Planet is asking, what makes a magnetic stellar or planetary north? The equivalent of a common magnet's north? Yeah, so tell us a little bit about, how do you know which one is north and south, and does everything have two poles? Like, so, what makes the sun's magnetic field north, and what makes...
Well, by convention, we define the sun's north and south hemispheres by the rotation axis. And the rotation, as Claire said again, is differential. So the equator is very clearly defined as the fast-moving band between the two poles of the rotation axis. And the magnetic poles actually oscillate with the solar cycle in antiphase with the sunspots. So there is no permanent north pole in the sense of magnetism. There's no permanent positive pole. The pole flips every 11 years in antiphase with the sunspots. So we do have to distinguish these two conventions, the magnetic.
So it's just a convention. And the Earth's magnetic field, too, apparently flips.
Yeah, a much longer period.
Yeah, a much longer period. Adam Synergy, isn't the Parker Solar Probe going to study the corona when it gets close to the sun?
Absolutely. It'll get very close.
Why don't you tell us a little bit about the Parker Solar Probe?
Yeah, what is it?
So it's a spacecraft. It'll give us in situ measurements, by which I mean it won't be remote sensed images. It'll be diagnostics of the solar plasma.
It's going in.
Going in, yeah. And it's having a good sense of what the plasma is doing right where it's at. It'll get as close as 4% of the Earth's distance from the sun. So unprecedentedly close by a very large margin. And it'll explore parts of the corona very directly that we can only image at this point.
Yeah, and when I was working at HAO, one thing I learned was just how hard it is to measure the magnetic field of the sun. In fact, we really can only do with magnetic fields like what we do with dark matter. We can really only infer the existence of the magnetic field by what we can see. In this case, the solar plasma of the corona shows us the field lines. But measuring the strength of the magnetic field is actually a hard measurement to make, isn't it? You need to really be there with I don't know, what measures magnetic fields? What's it called?
Magnetometer.
Magnetometer. Okay, so so you need to go in there with one of those little probes, and I'm glad I can crack you up, Carol. Magnetometer. Okay. Magnetometer. And measure it directly. It's hard to get it any other way, isn't there?
Well, that's the only way you can get a direct measurement of the field, is to go in. Otherwise, as you say, we're relying on remote sensed measurements taken in wavelength and position, and we have to invert these signals using models. And eventually we end up with a magnetic field diagnostic, which we have to be careful about being too confident with. Whereas if you send an instrument in directly, there's no ambiguity.
Yeah, and Susan Hunt, Cello Fingers is commenting, so the magnetic lines are basically a map of direction for plasma ejection to follow, and National Solar Observatory is here commenting that's about it. So the magnetic lines basically are they're a line of where the plasma ejection can go. Unless you said something briefly about CMEs, coronal mass ejections, these are magnetic eruptions, aren't they?
Exactly. Yes.
And how powerful could they be? I mean, give us an idea of just how these are solar eruptions, but can they harm Earth? You mentioned about solar grids earlier. What other kinds of things can they do to Earth?
Well, these eruptions are moving magnetic fields, and as any physicist knows, a moving field induces an electric current, and it's really the current that causes the damage. If one of these finds its way into a power grid, then there's no way of controlling that if you don't shut down the grid in time. So that's the main danger from these ejections on Earth. Mm-hmm. There's also the danger of energetic particles, which could travel along the field lines very, very quickly, close to the speed of light, some significant fraction of the speed of light. These are the things that astronauts and people behind satellites worry about, because they can really do harm there, as well as the ejections.
Yeah, Andrew Planet is asking me if I'm going to be streaming the Eclipse live. I'm going to try. I'm going to go to South Carolina if I can get there. I'm worried about traffic now. So I guess with some time that we have left, I want to ask you guys to give us some advice on how to observe this eclipse. Now, I put a link to the AAS safety page in the description box of this hangout, so you can definitely go there. But let's talk a little bit about, what advice do you have for people who are trying to go see this eclipse themselves?
Leave early.
Mm-hmm.
Yeah, no kidding. It's really going to be bad.
Traffic on Eclipse Day is going to be a mess. So if you can leave on Sunday, or even better would be on Saturday, and get to where you're going, make sure you bring lots of supplies. They're expecting grocery stores to be sold out and petrol pumps to be sold out. So fill a tank full of gas and stick it in your trunk just in case. As far as the actual mechanism for viewing the eclipse itself, during the partial phases, so everybody in the entire country will have the opportunity to see a partial eclipse, even if you're on the path of totality. And during the partial phases of the eclipse, you need to have eye protection. So you need to have either a solar filter for your telescope, you need to have a pair of trusty eclipse glasses. Make sure if you have eclipse glasses that they come from a reputable vendor. There are counterfeit eclipse glasses flooding the internet at the moment. The AAS actually has a list of verified vendors, so we recommend that you go to them.
Yep.
A lot of people, a lot of organizations are giving away solar eclipse glasses, so you can try and get your hands on some of them. If you have a telescope, make sure that you have a well-fitting solar filter for the front of your telescope. If you have a nighttime telescope with no solar filter, you can build a sun funnel, which is pretty easy to make. I have one here somewhere. I'll go find it in just a second. And they're basically made out of an oil funnel for your car and some layered up shower curtain material, and it projects the view of the sun onto the sun funnel. It's a really safe way of making sure that you get to see the eclipse without having running the risk of anybody doing damage to their eyes.
I've never heard of that. I'm going to have to look that up. Sun funnel. That sounds fun.
Yeah, Rick Feinberg put it together from the AAS, the press officer. So we have a video showing how to do it. That might be helpful, and I can just on the other side of my office. I'll go grab it in just a second. The key really is that no matter what you do, you need to make sure that your solar filter is on the front end of your instrument. So whether your instrument is a camera, a telescope, or just your eyeballs, you make sure that the filter is on the front, blocking all of the light, or most of the light, before it goes through any optics. So for example, if you have a camera within a viewfinder, it's not safe for you to put Eclipse glasses on and then look through the viewfinder, because all of that light is still coming directly through your camera. The filter has to go on the front side of your camera. A really cheap and easy way, and this is really fun during the partial phases, is to use a pinhole viewer. So this is literally just a piece of card with a drawing pin or a poster pin that you just poke a little hole through, and then you can look at the shape of the sun. So this is especially interesting during the crescent phases. You can look at the shadow that's cast by this on the ground or on a piece of card. So be careful if you're using a pinhole viewer. You don't look at this directly through the pinhole. You let the light shine through the pinhole, and you look at the projected light on a piece of card or on the ground or something like that. And you don't even have to have something specific for that. You can cross your fingers, interlacing your fingers like this, and looking at each of the little holes then becomes a pinhole, and you can see the crescent shape take the shadow of your hands will create a crescent shape. Or the leaves on trees will do the same.
Leaves on trees are really, that's really fun.
I expect my curls to have pinhole projections.
We want a photograph of that.
Yeah, that'll so everything that has just anything that can be like a dime size or smaller could be considered a pinhole in this case, and you can use that to see the crescent shape. Once, if you are fortunate enough to be on the path of totality, once you see Bailey's beads and then the diamond ring, once the diamond ring goes away, that's totality. And that is where you can take off your solar filters, take off your eclipse glasses, and look directly at the sun only during this 2-minute period of totality to see the solar corona. If you keep your solar filters on, you're not going to see anything. So you've got to take all of these off. You have 2 minutes to be able to observe the solar corona. And then when the diamond ring comes back, you got to make sure your filters and your eclipse glasses are already back on. So make sure you've got your timing down. It's going to be very well understood, the timing of the eclipse at every point. We have an interactive eclipse map that I might call on Carl to share really quick, where you can click on any point in the United States, and it will give you the timing of the eclipse on that at that particular location. So let's see.
I'm sure he's not got it up yet.
There we go. Where's the map? I know I have it on here somewhere.
So
oh no!
Do you want the URL again?
No, just
I'm also, while you're getting it up, I'll just let people know I'm making a video tomorrow, which I'll be posting about. I'm going to be showing people different ways of observing the sun too. I'll have my astro scan out where I'll do eyepiece projection. I'll do pinhole. I'm going to build a funnel now, a sun funnel. Let me check that out. That looks really
sun funnel.
Great.
So it's fairly rudimentary. The really important thing is that whatever eyepiece you choose to use, it has to be completely made out of metal. There can't be any plastic in it, or it will melt.
Oh, jeez.
So you've got to make sure that this is taking the brunt of all of the heat. And then on here you have either layers of shower curtain. We have some back projection material. There's a bunch of stuff that you can use.
Okay, can you hold that up again? I was busy.
Sure.
Carl shared the screen right when you were. Okay, so that's just shower material. Looks like a hose clamp.
A hose clamp. This is a funnel for your oil for your car. You just cut the end off it, and then on here is the eyepiece for a telescope made completely of metal. So the AAS has a great guide. Written guide, and we've just done a video demonstration of this. So if you, the NSO actually has been doing a lot of work in the last year to help people prepare for the eclipse. we have a series of webcasts that might be useful for folks. Each webcast has an introduction to some element of solar physics and how it relates to the eclipse. It then has a demonstration of an activity you can do around the eclipse, either on eclipse day or before or after. And then we have an invited guest speaker for about 10 minutes where they'll talk about their research and how it relates to the solar eclipse. And as part of this web series, we also have how to make a sun funnel.
Go check them out, folks. That sounds like a great resource. National Solar Observatory.
And we need tweets during the eclipse where Gordon tells us whether he's being smug or happy.
I'm always smug.
Oh, you're always smug. Okay.
I see that we have the interactive eclipse map here.
All right,
so this
get it up.
This is on the NSO webpage, so eclipse2017.nso.edu. And then from there, you can click on the eclipse map. And if you wouldn't mind clicking on a location, Carl, we have the timing of the eclipse at every location in local time.
Yay!
Yay!
One of the benefits of this, a lot of the interactive eclipse maps give you the universal time, so you got to convert your time. But we tried to make it local, so it was easy for folks.
That's good.
Oh, good. So times are local. That's nice.
Times are local. If you're in South Carolina, if you go back to South Carolina there till we just have a look, you can see the timing of your totality, so you know when you can take off your eclipse glasses and when they got to be back on by. So you take off your eclipse glasses at 2:44 and 50 seconds, and they got to go back on again by 2:46 and 49 seconds. So that gives you about exactly 3 minutes. That's probably one of the longest periods of totality.
Yeah, that's nice.
Oh, sorry, 2 minutes. 2 minutes and 58 seconds. So that's all you got. I also have heard, so this is my first solar eclipse. I have never seen totality before, and I'm really excited. And I was advised by a veteran eclipse viewer, eclipse chaser, to not worry about trying to take photographs during totality, that the chances are that you will be fiddling with equipment and you will miss a really short 2-minute period of totality. So if you can set your equipment that it will take pictures automatically for you, then absolutely go right ahead. But to prioritize just looking at the eclipse with your eyes, and that there will be tons and tons of professionals who will be sharing eclipse pictures after the eclipse is over, so there'll be lots of really good quality ones, but to be careful that 2 minutes goes by in the blink of an eye, and you don't want to miss that because you've been messing around with your camera exposure.
Yeah, leave that to the professionals. There's lots of astronomers. You've got Matt Pennant et al. You got their stream of observations they're going to be making. Just enjoy it. Just look up. Just go up and enjoy it.
And you have plenty of time before totality to take those pinhole camera pictures through leaves, through Claire's hair,
That's
and
exactly
other creative things. Yeah.
So that's good advice. Okay, well, all right. Well, let's see, Adam. So I just want to say real quick, Adam Synergy, I expect you to build me one of those sun funnels. I think those are awesome. You should make one so I can see what they're like up close. So maybe in time for our next hangout. Okay, so that is. Let's talk about the future. You guys are going, and Clara, you wanted to get a chance to talk about this too. Where are we heading with solar observatory, solar research? I know we have the AT. I'm sorry, it's not the ATST anymore. Say it again. What's the name of the
Daniel K. Inouye Solar Telescope. We call it DKIST for short.
DKIST. There's a DKIST ground-based observatory coming up, and you mentioned something before the hangout started about something else. Was that it?
I think it was just
was
DKIST.
Was that just DKIST? Okay, I'm sorry. There was another. I thought there was another. So yes,
I think we mentioned the fact that DKIST had a coronagraph, but we've already sort of touched on that. So we're about to embark on the next phase of solar observations. Between the Parker Solar Probe and DKIST, we're facing into the unknown. There is so much about the sun that remains totally unanswered, not least of which is why the corona is 1 million degrees or more. And so the new set of observations that will come from the solar probe and DKIST combination are really going to push us into the next century. There's so much that we can't even fathom that these two instruments will bring together. DKIST will be the most powerful solar telescope in the whole world when it's built. It will be, we have a 4-meter mirror on this telescope. And for comparison, the current largest solar telescope in the world is 1.6 meters. So we're more than doubling the mirror size. So if you think about the mirror as being a giant collecting bucket, just the sheer number of photons that we're going to be able to collect with this new telescope is just going to, it's literally.
Is the current large one in Arizona?
No, it's in Big Bear in California.
Sure.
Yeah. So it's the new solar telescope in Big Bear.
Okay, I want to try and get one more quick question in because it's a good one. Cello Fingers is asking: is anybody going to repeat the Einstein experiment of observing the sun's gravity bending starlight during the eclipse? This was one of the this was actually important for relativity. Einstein wanted observations of Mercury's light as it went close to the sun. Is anybody going to be doing stuff like that? Do you guys know?
I vaguely remember reading that somebody is, but I forget the name.
Okay, yeah.
I'd heard that Sonoma State University was planning to repeat the experiment, but that was about a year and a half ago, and I don't know what the status of that is, if they have decided to go ahead with it.
I wonder if Mercury is in a favorable position to do that or not. That just happened to be something that he needed as for confirmation of the fact that gravity bends space-time, and so if it did, then it would affect the light paths of some things getting very, very close to the sun. So okay, well, this is great, guys. Thank you all both so much for taking time out to talk to us about your observations. I don't know, Gordon, should I be wishing you smugness or not? You
it's not a very good thing to encourage in a person.
Very true.
You could wish me a learning experience.
Yeah, socially, it's not going to help you with your friends. But I mean, should I wish for you success or failure in your?
A bit of both. Everything in moderation.
I think success is he gets to modify his model.
Yeah. Either way, you're happy.
Win-win.
That's the best science of all.
We love it.
Yeah, that's the best science of all.
Because even if it exactly matches, he's going to then say, "That's not right. It can't exactly match. There are too many simplifications.
That's not going to happen,
right? That's not going to happen. But if it did, you would still be like, wait a minute."
Yeah.
So Gordon would be walking down the hall. I got it right. I got it right.
I would faint.
Okay, folks. Well, thank you all so much, and I'll go ahead. I'll go ahead and stop it there. I want to, on behalf of all of our guests and Dr. Carol Christian from the Center for Emerging Media, we also have Dr. Claire Raftery she's the director of the Education of Public Outreach at the National Solar Observatory. Dr. Gordon Petrie, he's a scientist at NSO and has been making predictions about what he thinks is going to happen during the solar eclipse on August 21st, 2017. We hope you guys, if you're in the United States, get a chance to look up at least once during the day. You'll see something, maybe not directly at it, but using the safety tips that we have outlined in this hangout and in other places. I want to thank all of you for watching, and as always, keep looking up.
Thank you.